So how do we work out the value for the inductor? We want an inductor which has got a value which is sufficient to achieve a high enough impedance for the microwaves not to be able to flow back into the power supply. So I'm going to put a voltage and current meter here at my power supply so I can see what actually goes back into it. And also I'm going to look at the current and voltage that come from my RF source right here on the other side of the capacitor. So let's make a little bit of space by shifting this arrangement back a little bit. And then we can have a current meter in the right place. So let's press Ctrl L and select I meter. And then place it right here in series with the source. And then we'll reconnect the bias to the base. And then we'll also put a voltmeter at this point as well. So we'll press Ctrl L and select V meter. So we can see both voltage and current at the input, and we can compare them to the voltage and current that flow back into the power supply. So up at the top here, take away this connection and replace it with a current meter, so with an I meter. And then, of course, and we can't put a voltage meter right here because it's just a DC source. What we would see would just be the 3 volts. But the fact that we have some current flowing back into the power supply would create some sort of ripple on the voltage across this resistor. So this is the voltage that we want to see, the voltage that will appear at the collector of our transistor. So let's press Ctrl L and select a V meter. And then we'll just place it right here at this node. So now you can see that we've got a voltmeter and a current meter at the input to see what RF signals we're getting through. And then we've got a current meter in series with my power supply, so I can see if there is any RF current that flows back into it. And also we've got a voltmeter which will give us the voltage across the resistor RC1, and then it will give us an indication of whether there are fluctuations in the bias that we're feeding to our collector. Now, a couple of other things. Of course, these 2 inductors will need to be the same, as they're just related to the frequency I'm operating at. And hence, I can just use one value for both of them. And instead of having to modify them both, I can just introduce a variable in my schematic and assign the value of the inductance to this variable. So I can just click on the equation block here, and then just say, for example, LC equals 1, so the inductance of my choke, LC equals to 1, and then I can just use this variable LC and assign it to the inductance of my 2 RF chokes. The other thing that I can do is make this variable tunable, so that then once we get to seeing what changes we get in the RF current and voltages that we see in the circuit, we can just tune both of the RF chokes together. So let's click on the screwdriver, on the tune tool, and then on this variable here. Now we're almost there. The last thing that we need to do is to change this port into a harmonic balance port. The reason for this is that we want to be able to see the time domain waveforms of current and voltage, and this can't be done with this sort of port. We need to replace port 1 with a harmonic balance port. So let's just get rid of it, and then click on the port SRC up here, and then place it on the schematic like so. So this port is exactly the same as the other one in our case. It's not going to give us any specific advantage. It's just that we need to use it to be able to visualize the time domain waveform. It's just one of the quirks of the microwave office simulator. So you can see that this port has got a 50 ohm internal impedance. You can specify harmonics with this port, for example, harmonics of your signal and their power. You can specify the power that you want this port to have. You can specify the initial angle of your RF waveform. So we'll just set a power of -20 dBm here, just because this is going to work well with this kind of bias levels that we've got for our transistor. And so we've replaced our port with a similar element which is more complex and allows the simulator to then display the time waveforms. So it's time to go back to our graphs now and then select new graph, a rectangular graph, and we'll call it RF currents. We'll right click on it, go on to add a new measurement, and then we'll have to go, of course, to the nonlinear measurements. Select current, and then we'll select I time, and we'll select the schematic that this comes from, and that's of course the S parameter measurement, and the measuring component will be the input ammeter, which is I-meter 1, and click on apply. And then of course we also want to see the current that flows back into the power supply, and that's given by I-meter 2, and click on apply, and then simulate. So first of all, you can see that the curves are quite distorted, and that is because we're using a nonlinear element, which is our transistor, and this obviously makes the waveform different from what they would normally be if they were going through a simple passive load. Also, you can see that there is an appreciable quantity of current that goes back into our power supply. And so, well, we have to be careful with this, because this creates a considerable ripple in a DC current that should not have any RF ripple at all. And this would create havoc with our bias, and also may potentially destabilize our transistor and cause oscillations and all manner of problems. So let's have a look at the voltages as well. Create a new graph, a rectangular graph. We'll call it RF voltage. And then we right click on here, go on to add a new measurement. We want a nonlinear measurement, voltage. We'll go to V time, and then our measurement component will be VM1 for the input, and VM2 for our collector voltage, and then click on OK and simulate. So the pink curve represents the voltage at our collector terminal. And you can see how this voltage exhibits a considerable level of fluctuation, and that is because it's got an RF ripple of the frequency which we're operating at superimposed upon its DC level. And this can create a lot of trouble, because of course the bias of the transistor is then not stable, and all these fluctuations in the bias may create some oscillations with the transistor, may make it unstable and hence operating efficiently. So there's all manner of trouble that can be stirred by this sort of thing. Now if we just close all the windows, and then we just reopen the RF voltage and RF current ones, and we tile them vertically, then we can see them both at the same time. So the blue curves represent voltage and current at the input, and the pink curves represent the current that is flowing back into the power supply, and then the voltage which is at the collector terminal of our transistor. And you can see that the situation is not good now. So what we can do is open the tuner, which allows us to then tune the variable LC, which represents the inductance of both our RF chokes, and see what we can do to eliminate or diminish the ripple that we're seeing to a level which is acceptable. First of all, let's select the appropriate range for our inductor. Let's start from 10 nanohenries and go up to, say, 800 nanohenries. And now as we increase the value of the inductor, you can see how the current ripple is flattening, and so is the voltage ripple. And as we go up and up and up, you can see they're getting much, much flatter. So ideally, if you go really far up, then they still exhibit a little bit of ripple, but very minimal. Usually it is found, particularly this frequency, that for values beyond about 270, 300, you don't get much of an improvement. So for us, we can just set the inductor to about 270 nanohenries, and then we get a decent result. Inasmuch as it may appear that if you get a higher value, you then get a better result. That is not always the case, because with inductor, just as with capacitors, you get some parasitic capacitance for any real practical inductor. So because you've got this stray capacitance which comes from the physical construction of your inductor, then you won't get as much benefit as you may think by going up beyond a certain value for your RF choke. So we have seen how we can use an inductor of 270 nanohenries or more to avoid the high frequency signals flowing back into our bias network and into our power supply. As before, we now have a look at how things change when we use a non-ideal inductor, a real inductor, for our RF chokes. So let's go back to our schematic, and then we'll change these two inductors for real inductors that we can find in the libraries of Microwave Office. So let's get rid of these two and go to Elements, and then scroll down to Libraries, and this time we'll look for a vendor that does passive components, and that's Coilcraft. Select Inductor, and we'll go for Chip Inductors and Models, and we'll choose the 0805 CS series, and we'll first pick an inductor of 270 nanohenries, just the same value as we picked before. So drag that onto the schematic, and then rotate and click to place, and connect it back to the terminals. Then we can press Ctrl C and Ctrl V to create a copy of this and place another one in series with the collector. Okay, now let's go back to our project tab and then simulate, and yet again we can just close the schematic and then display our current and voltage graphs side to side by going into Window, Tile Vertical. You can see that there is a little bit more ripple than we had with the ideal inductor. That's to be expected, but it is still acceptable. Now what I'm going to do is create a copy of the schematic in the usual way. So we'll just drag the S parameter measurement schematic onto the circuit schematics heading, and then we'll rename the schematic. We'll name it larger choke. And then on this new schematic that we've created, which is exactly identical, this time we'll replace our choke with a bigger inductor and see what effects we get. So let's go back to Elements, and then you can see we've got an 820 nanohenry inductor there. So we can just clear these two and get ourselves an 820 nanohenries real inductor and replace our chokes with it. Press Ctrl C and Ctrl V to create a copy and put it in series with the collector. Okay, great. Let's go back to project options now, and we'll go to the RF current graph first, and we want to add the same measurements that we've got here for the original schematic with the 270 nanohenries inductor for the other schematic as well, so we can compare directly. So let's right click, go on to add a new measurement, and then we'll pick the schematic as S-parameter large choke, and we'll of course want to measure the current, and it will be I time, and again we'll want to see it at the input and also at the power supply terminal, and then simulate. You can see that you don't get much of an advantage by using a larger choke. In fact, if anything, the ripple is slightly bigger than it was before. So really sometimes when you're looking at things in the real world, you can't just go up and up and up and choose a bigger value and disregard completely the parasitics, because those two have an effect. And in this case in particular, you can see that an 820 nanohenries inductor would have been a poor choice because you didn't need it. You could have gotten away with the 270 nanohenry ones. We can, just for completeness, look at the voltage as well. Again, we'll go to add a new measurement, and we'll select V time in this case. So we'll go to voltage and then V time, and the measurement components will be VM1 and VM2. And then we can simulate it again. And you can see that the voltage at the collector terminal has again a similar ripple. So again, this confirms that 270 nanohenries is sufficient for our purposes. So we can delete the second schematic now. We don't need this anymore. And also since we have now selected the correct value of inductance, we can get rid of the graphs for the current and the voltage just to make things not quite as busy. So let's go back to our schematic here. So now we've got capacitors in place that avoid the DC bias network being loaded by the impedance of our RF sources. And also we've got RF chokes that prevent the RF signals to go back into my bias network and up to the power supply and modulate the bias voltages. So we are in a safe place to be able to measure the S parameters of these transistors. We've seen what S parameters are about. They obviously can measure the reflection coefficient, which is what we've used them for the passive circuits. And from the reflection coefficient you get the impedance seen at a particular port, but also they can measure the power transferred between one port and another. And this is another measurement that's obviously very interesting when you're designing amplifiers, because you want to see the power that you can transfer from one port to another. Now that we don't need to see ref time waveforms anymore, we can just get rid of the harmonic balance port here and just add a simple test port as we usually do. So now we've got our port 1 here and our port 2 here at the output, which is connected to the collector of the transistor, and we want to see the S parameters that we can measure for this two-port network. This is really quite an easy measurement now. The important thing was biasing the transistor correctly and also choosing the right components to isolate DC and RF. And now we just really can represent our S parameters whichever way we like. We are used to representing S11 on a Smith chart, but in this case, because subsequently we will be using equations which require numerical data, it would be advisable to have our results in a tabular form. And we can simply do that by right-clicking on graphs and then choosing a new graph, and this time the type will be tabular. So it's not really a graph, it's a table, but because it's an output, so it's a way to represent the data, then it is under the graphs. And so we'll call this S parameters. And now we can just right-click on this blank canvas to add our measurements. So we want to go back to the linear measurements now, and to the port parameters and the S parameters. And we want to get them from S parameter measurement schematic. And now we can add S11 by clicking on apply, and then S21, which measures the power transferred to the output from the input, and then S12, which looks at the reverse power from the output flowing back into the input, and then S22, which is the reflection coefficient at the output, and then click on OK. Now simulate. You can see that since we've chosen a complex format for S parameters, we're getting the real and imaginary part for each parameter that we decided to measure. However, it is more useful to have these parameters represented in terms of magnitude and angle, and we can do this quite easily by right-clicking, going on to Properties, and then we can choose to have the display format as magnitude and angle. Click on OK, and then you can see now the S parameters at 1900 MHz, 1.9 gigs, are displayed in a tabular form. So we got the S11 in magnitude and phase, same thing for the S21, and so on. Notice that whereas S11 and S22 are reflection coefficients, and hence they are actually limited to having a magnitude less than unity, the S21, which represents the gain, has got a magnitude which is higher than unity. Now, two things here. These are not set in stone. The S11 and S22 parameters may become greater than unity since you have an active circuit, but when that happens you end up having feedback effects, and this can cause oscillations, so that's really bad news. Also, the S21, when you have a transistor which is not matched, and so you've just measured the S parameters with 50 ohm terminations, which may mean that the transistor is not operating in a region where it can provide gain, the S21 may also be less than 1. So these are just a few pointers to bear in mind. Also, we may want, for example, to export these S parameter values to another program or to an Excel spreadsheet if we wanted to. And we can just click on Graph and then export trace data, and then we can just select a name for the file. We can just call it BFP405 or 1900 megahertz as parameters. We can open this file by double clicking on it, and you can see that a text file has been created which we could easily import into Excel if we wanted to. Now the other thing that we could have done to copy it into Excel is just go on to Edit and select All to Clipboard, then go back to Excel and then paste, and again you get a similar result. So this just shows how easy it is to transfer data out of Microwave Office. So now we biased our transistor and measured its test parameters, and in the next tutorials we will be looking at different ways to design an amplifier based on this network.